Good afternoon and good morning, everybody. I'm Marcello Schiavina, GIS expert for the European Commission Directorate General for Regional and Urban Policies. After Martino's presentation on the foundations of the GHSL, I will show you how we added information to the built-up distribution by producing the population distribution grids and how we generated knowledge of human settlement characteristics across the globe by applying the degree of urbanization methodology. So I will quickly introduce you to the concept of population grid and show you how we implemented it in the GHSL framework with a couple of details of the large process we followed to produce the global multitemporal GHS POP grids. And then I will present you briefly the degree of urbanization methodology and how we ported this into the GHSL framework, showing you the application of this method to generate the settlement grid GHS SMOD and the territorial unit classification GHS DUC. So let's start from the population grid concept, what it is, why we need it, and how it can be produced. A population grid is a representation of the population distribution on a regular grid. These grids are usually in raster format, but for small areas, a single region or a country could be also in vector format. Each cell represents the number of people in that area, and according to the population concept used, they can be resident people, daytime population, or ambient population, that is the average between daytime and nighttime population. In the case of equal area projections, the count represents also the density of the population per cell. But why a population grid is very useful? Well, because the representation does not depend on the shape and the size of the unit, preventing the well-known modifiable areal unit problem. As in the figure shown, where on the left, the representation of the density using, for example, municipality units hides the presence of a dense settlement, well delineated using the grid on the right. Moreover, regular grids are stable over time, allowing the analysis of changes and dynamics. And they also integrate more easily with other data by assembling cells into any custom zone. Okay, but how it is produced? There are different ways to produce a regular population grid, and most depend on the typology of available data. Most common case is the disaggregation from polygon units into grid by means of auxiliary layers correlated with population presence. For example, built-up surface or volume, like we do in GHSL, or more complex layer obtained by machine learning procedure, as WordPop does. Another possibility is the bottom-up approach by aggregating geocoded census point data or implementing a bespoke approach that uses a very accurate sample of census data to derive a statistical model and infer the population counts from statistical relationship found in the sample area extended to the whole area of interest. But let's see what we did in the production of the GHS POP grids, what we used as input data, what was the general workflow, and a focus on multitemporal population estimate model and the selection of the covariate. GHS POP main input is the resident population census data collected by CIESIN. This data cover the whole populated area of the globe, subdivided in 251 countries for more than 13 million polygons. CIESIN harmonized the geometries and provided us with two values of population counts per polygon in two separate census campaigns of the country, plus a derived annual growth rate from an exponential growth model. Then we used the World Population Prospects 2022 to reconcile the total country's population to the UN multitemporal country statistics, and the World Urbanization Prospect 2018 to exploit the time series of population in cities and urban agglomerations. Finally, last inputs are the GHSL built-up layers as ancillary layers for the top-down disaggregation method. This is the detailed workflow we developed. Well, you can check the detailed steps in the PDF presentation shared after this lecture or in the paper. But in broad terms, we took the CIESIN data and we performed data analysis and pre-processing to compile input metadata and align the geometry to the UN country list. We developed a model to estimate the time series of population per units based on the standard approach of CIESIN, that is a simple exponential model that uses the estimated growth rate and rescale country totals to the WPP values. But we added a step by bounding time series to WUP cities and urban agglomeration data. We will see some details in the next slides. We extended the coastline to take into account misalignments of seas in coastline geometry with our built-up detection, also to avoid missing reclaimed land in some areas of the world. We revised systematically the census data, challenging the unpopulated data, and detecting and fixing some, unfortunately not all, anomalies. For example, unpopulated units where satellite images provided evidence of human presence were split and merged with adjacent population units, or large anomalies were identified, for example, in EU, by comparing the season population counts with a long time series of low estimated population data from Eurostat. We identified also shifted units where population data were exchanged or even wrongly reported data. We selected the best covariate among the GHSL built-up layers using independent census data. And finally, sorry, okay. And finally, we performed the downscaling of population estimate for each unit to the final grid, showing the distribution of population from 1975 to 2030 in 5 years interval at 100-meter equal area mole-wide projection. The produced grids were also tested against independent data for quality check and assessment, but this will be one of the topics of the next lecture by my colleague, Johannes. Here, few details on the population estimate model. Basically, this is the scheme of the CSN model, where the exponential growth is applied to each unit, and then the population is scaled uniformly across units in each country and at each epoch to match the WPP totals per country and epoch. We introduced the further step, adding a previous anchor point to a subset of the country units. Basically, before scaling at country level, we selected the groups of units belonging to the same city or urban agglomeration to match the WUP totals per epoch. This step seems easy, but there were lots of challenges. First of all, WUP cities and urban agglomeration, and here I add that we used an extended and published version of the database, gently shared by Imendesa, counting more than 4,000 cities. Well, these WUP cities and agglomeration are located in the world only as points with lat-long coordinates. So after a revision of the locations through geocoding and reverse geocoding, filtering unreliable places and removing overlapping definition of metro areas and urban agglomeration in the same area, we had to estimate the boundaries. So from the CSN unit identified by the WUP city coordinate, we aggregated adjacent units until we reach, by summing the population of these units in the most recent census year, the value reported in the WUP for the very same year. This was performed by using the smart dissolve methodology to aggregate units to reach a target field value threshold. In the figure, you can see an example in US, one of the few places where the actual urban agglomeration boundaries were available, comparing the estimated boundaries in blue with the actual ones. The matching is quite good, but there is an approximation. WUP stats are reported using changing boundaries, while our approach estimates boundaries in a single time step, and we kept this fixed through the whole 1975-2030 time horizon. For this reason, but also because the aggregation did not provide perfect match between CSN units sample of population and the imposed threshold for WUP population data, we had the discrepancies between WUP population of a city and the aggregated unit sum of population. And these discrepancies were also different in the two census epochs. However, we exploited these different discrepancies to rescale the WUP time series and mitigate the fixed boundaries approximation. If the past CSN population was much higher than the WUP reported for that year, we suppose that at the epoch, the boundaries might have been smaller, and WUP population time series should then increase to reflect the actual units we were using. So We implemented a nonlinear rescaling based on the discrepancies in the two CSNA census epochs with parameters calibrated on a set of countries for which independent census data were available, plus a smaller set for validation. This table shows you the increased performances with respect to the standard CSN exponential model that was the baseline, basically, of previous GHS POP grids and other population grids produced by other groups. Finally, we performed some testing to select the best covariate to downscale the population estimates from units to grid. We took some independent census data from some countries. We aggregated the data at the most similar average area of our CSN geometry, input geometry, and we downscaled from the aggregated polygons using alternative covariates, and then compared the downscaling performances at highest available census resolution. As covariate, we tested the total surface or volume, the pure residential surface or volume obtained by fully removing the non-residential component from the total built-up, and two mixed models where the non-residential component is only partly removed by means of weighting and or binarizing the non-residential component through an analysis of densities in pure residential and pure non-residential census unit. These mixed approach were tested to mitigate basically the presence of mixed function buildings. The results we obtained were strongly in favor of our GHSL built-up volume, purely residential. So the GHS built V total minus the non-residential component was selected as target layer for the production of the GHS POP. So let's have a look. So here are some images of the process in the area of Bangkok, Thailand. Here you see the built-up volume in black, the total minus the residential that is purple. And this was our ancillary layer. Then we have the CSN input in the same area. You see the polygon with the population density from the census round of 2010 in Thailand. Then we have the estimate procedure by delineating the WP cities and urban agglomeration boundaries here in blue. And then to obtain, let's say, the final estimated population counts per unit. And finally, the output in an increased resolution from the input unit obtained by downscaling from census polygon to the 100-meter grid. And this for all 5 years intervals between 1975 and 2030. These grids were also, are also provided as aggregation at 1 kilometer, especially for the next step I'm going to show you. As promised here, a small step beyond, transforming the information of population distribution into the knowledge of the human settlement classified by the degree of urbanization methodology. But let's start briefly introducing you the concept of this methodology. So what it is, why it is needed, and how it is implemented. So the degree of urbanization, or the GURBA, is an harmonized people-based definition of the urban-rural continuum that goes beyond the pure urban-rural dichotomy by introducing an intermediate class that accommodates the differences in the interpretation of what is urban or rural across the globe. For a total of 3 classes at level 1, then is further split into 7 classes at level 2. It is based on an equal area 1 kilometer population grid and has 2 stages. First, the production of a settlement grid, and second, from this to the classification of territorial units, so polygons, to link the GURBA classes to other statistics collected at such polygon level, allowing their disaggregation by the GURBA. Since March 2020, this is the recommended methodology by the UN Statistical Commission to delineate urban and rural areas for international comparison, especially in the context of sustainable development goals. So by reaching the stage 2, it is possible to report statistics relevant for the SDGs collected at a given territorial unit level by the GURBA. Why this method is really needed and we cannot rely on national definitions of urban and rural? Well, it is quite simple. Countries do have very different definitions based on population density or other indicators, but also purely designated by national authorities, making very difficult to compare statistics across the globe. Imagine comparing statistics for a city in Denmark, where a city is defined by areas with at least 200 inhabitants, with those of a city in China, where the population threshold is set to 100,000. Not exactly the same thing. So, very quickly, how the Regurba works. It is based on a regular 1 kilometer equal area population grid, using thresholds of population densities to select grid cells. Then adjacent cells holding the required density are grouped together using contiguity rules to form contiguous clusters of cells. And the total population of this cluster is tested for a minimum total population size. All cells belonging to a given cluster of pixels with a given density and size greater than a minimum are classified in one of the Regurba classes. And here, the three classes at level 1, urban centers, with at least 1,500 people per square kilometer and at least 50,000 people, urban clusters with at least 300 people per square kilometer and at least 5,000 people, with residual as rural areas. Both urban clusters and rural grid cells are split into three classes nested at level 2, providing a more nuanced classification that is able to distinguish actual settlements like dense, semi-dense urban clusters and villages from the suburban peri-urban areas surrounding the settlements and the low-density rural areas. Once the settlement grid is produced, by combining this with the population grid, it is possible to count people in each territorial unit that lives in the different Regurba classes. Then, by applying simple majority rules within each unit, the unit can be classified in the most relevant Regurba class. At stage 2, the names are slightly different, let's say more common, so city, towns, and villages, with level 1 splitting city, towns, and semi-dense area, and rural areas, and then we have a further, as in the stage 1, a further split into the 7 classes at level 2s. Well, so this is the methodology. So, and we applied both stage 1 and stage 2 to the GHS pop layer to obtain the settlement classification grid, the GHS SMOD, and the classified territorial units, GHS DUC. So the GHS mod is the simple application of the Regurba methodology to the population grid GHS pop 1 kilometer at each available epoch, while the territorial units are taken from the global administrative boundaries layer, GAADM, by combining GHS mod and the 100-meter GHS pop, and providing classified units for all countries. However, this exercise is just an example of because GAADM has let's say the finest administrative level per country varies a lot, and some countries do have quite coarse subdivision. Moreover, this step is useful when statistics are available at a given administrative level to disaggregate them by the Regurba. And this was not performed, as no statistics is available with GAADM. So usually countries do apply the stage 2 to the administrative level at which statistics are collected to then report them by the Regurba. However, this layer we produced can be useful for those countries where the full implementation for population from population grid to the territorial unit cannot be performed, or for researchers to perform analysis, as it can help to link the Regurba to country statistics without undergoing the full implementation. For example, this layer was used by Gallup World Poll to link the survey data to the Regurba and disaggregate the respondents' reply by the Regurba. So here we go back to our visual example of Bangkok, showing you another important feature of the GHSL implementing the degree of urbanization. That is the possibility to study the dynamics of settlements evolution. For example, here we are in 1980 with single urban center for Bangkok. And by progressing in time, we can go to 1990, and then to 2000, to 2010, to 2020, and also finally to 2030. So we have seen how the urban center of Bangkok expanded in 50 years with a growing peri-urban area, and how several other settlements are born meanwhile. So this is then what we get when we apply the Degurba Stage 2 classification to the GADM territorial units, as in our GHS DUC. Again, this step is very important to disaggregate the statistics by degree of urbanization, and can actually be used also to determine the administrative boundaries of a city or a town. As for example, in this figure, we can see the administrative boundaries of Bangkok. So to conclude, I can just show you a few global results derived from our GHS mod and the GHS pop layer, with the dynamic of the number of people per the Gurba class at level 1 from 1975 to 2020. Here we can see how the urban center population almost tripled in 45 years, urban cluster population almost doubled, actually as the total population of the world, while rural population remained constant. This meant an increase of the urban share, so the people share the living in urban areas as the sum of urban center and urban cluster population from 69% in 1975 to 80% in 2020. Especially this growth was present in urban center from 32% to 42% of the global population. And here a bit more disaggregated statistics by region. For example, we can see the huge increment in urban center population in Africa that increased from 96 millions to 550 millions people in 45 years, an almost six-fold increase. Or the quite stable population and population per class of the urban region. Or another interesting thing we can get from these results is the differences across the globe in the urbanization patterns. For example, South America, is very peculiar in its urbanization, as it is the region where the intermediate class shares are lowest, and they have the largest share of people living in urban center. In fact, when looking to the actual population distribution and settlement classification, these regions show very small peri-urban areas surrounding the urban centers. Or on the contrary, Asia, where there is the lowest share of rural population, 16%, even if almost equal the rural population of the rest of the world. But it has the highest share in the intermediate class, so 39%. So with this, I conclude, and I thank you for your interest and attention.